Thanks. I'm grateful to the organizers for the invitation out here. So since this is a meeting with philosophers and cosmologists, I thought it would be fun to start out with a philosopher. This is from the Critique of Pure Reason. There's this delightful part in it called the Antinomy of Pure Reason, where he proves both a bunch of theses and their antitheses. So the one that I remember well and made a slide for here is that the world has a beginning in time and limited in regard to space, and that it has no beginning or no limits in space, but is infinite. And he proves both of these, which is fun to see, and they're at various levels of persuasiveness. But what I find interesting is that the proofs that he gives are ones that some of them still kind of have that feeling that they might hold, and some of them are just clearly not true, given the understanding of space and time that we now have due to general relativity. So for example, when he says that the universe can't be finite because then it would have sort of an edge, and then if you go beyond that edge, what would there be but space? So it can't be finite. We now know that it's perfectly easy to create a model of the universe which is finite but unbounded, right? Like the closed FRW model. And he makes this sort of similar argument about not being able to have an infinite universe because you can't synthesize it. And this has echoes of some points that George made. And so I'm going to argue that general relativity also sort of undermines those. And I'm going to disagree in a lot of ways with the previous talk, because that'll be more fun. And in particular, I want to make a few claims that if we ask whether the universe is infinite in time to the future, and I'm going to call that an everlasting universe, I think that's likely on the basis of current cosmological data and theory. I think that if the universe is future eternal, that it's almost necessarily spatially infinite in a way that I'll describe. And then there's a question of whether it's eternal, that is infinite in the past as well, sort of timeless in some sense. And that, I think, will be maybe. And we'll see all three of those. So a lot of this is going to be based on the theory of inflation. Now, an amazing thing has happened over the past 20 years, which is that we have this sort of detailed, clear, and well-worked-out understanding of the last 13.7 billion years of cosmological evolution using a simple model. Wasn't easy to come up with, but is now you can write it on a T-shirt with about 6 parameters. And this explains sort of galaxy formation, the microwave background data, all kinds of stuff. And it's really a triumph, I think, of kind of physical thinking and the interplay between theory and experiment. But it does have some kind of initial conditions that are very fishy. So one way to term these is that the curvature scale of the universe, the physical curvature scale of space, divided by the sort of only natural scale you can build, the Planck scale, is really huge, much bigger than 10 to the 60 or so. The universe is primarily kind of GeV particles, like protons and neutrons, and smaller. Maybe there are dark matter particles that are somewhat larger, but if the universe started out with super high energy in a sort of Big Bang, where are the relics from that? You can easily make monopoles that should dominate the universe at this point. They're not seemingly there. Finally, the density, the variation in the density of the universe divided by the density fluctuations, are about a part in 100,000 on the Hubble scale. That is the scale of the observable universe, not the sort of natural number they might be of 1, which would lead to a black hole-dominated universe. But they're really tiny, and they're correlated across many causal horizons. That means that there are correlations and anti-correlations between regions of the universe that can have never had any causal contact if there were an initial singularity and sort of normal cosmological evolution 13.7 billion years ago. So what's been developed over the past 30 years, since about 1980, is that if we had a period of vacuum energy-driven exponential expansion, that's so-called inflation, then it basically solves these problems, at least in large part. It gives us a very big, nearly flat, homogeneous anisotropic universe. Big because it's exponential expansion. It takes the initial universe and makes it big. Flat because it stretches out the universe to decrease the curvature and increase the curvature scale. It tends to homogenize things by wiping away field gradients, by stretching them out, and by diluting particles away. It also dilutes away unwanted relics from the early phase. And as a natural byproduct, due to quantum fluctuations during the evolution of the fields driving inflation, it naturally gives you so-called scale-free trans-horizon correlated Gaussian adiabatic density fluctuations. That's a mouthful, but it's just the kind of density fluctuations that you observe in the microwave background radiation. So this is a map of the data, not a map, but rather a statistical characterization of the microwave background data from 9 years of the WMAP experiment. The WMAP experiment is here in black. These are two others, the South Pole Telescope and ACT, that go to smaller size regions on the sky. So small patches on the sky are to the right, and large patches on the sky are to the left. And this is the power, this is the sort of amplitude of the density fluctuations on these different scales. Now this curve that you can see underlying the data points is not a fit. Well, it's sort of a fit, but it is a model based on inflation and our understanding of the Big Bang evolution of the universe. And you can see that there's no way you're going to get this perfect of a fit by just an arbitrary curve with 6 parameters. You have to have the right model. But once you have that, you can then determine the 6 parameters from this, and actually a few more than 6. So for example, from this one, you conclude that the universe is basically flat. Omega curvature is 0.001 plus or minus 0.01. And there's also this interesting number called the spectral index. This is the departure from scale invariance for inflation aficionados, which is now detected. Inflation predicts that that number should not be 1. It should be a little less than 1. And it's now not 1 at 3 sigma using just the CMB data. If you add in other data, other astronomical data, you can get the same sort of consistent results with this, but with smaller error bars. So it turns into a 5 or 6 sigma result. So this plot will start going obsolete on Thursday when the Planck satellite announces initial results from that mission. And it'll be very interesting to see what that comes up with. My guess is, though, that it may come up with some interesting things, but a lot of what it will do is validate what WMAP has seen and make these error bars even smaller. So we've gotten to the point where there's very good sort of theoretical justification and observational support for this inflation model, to the point where we can actually start to look at individual inflation models and rule some of them out. Like this one is clearly ruled out by the data, this one somewhat, and so on. And as I said, this plot will get probably a lot better starting on Thursday when there's a lot more data. Now, it's relatively easy, at least at this point after 30 years of work, to take an inflation model. An inflation model, in many cases, is sort of a curve like this that says, as a function of some scalar field phi that permeates the universe, there's a vacuum energy v of phi. And once you have this, then that vacuum energy drives this exponential expansion. And the dynamics of the vacuum energy tell you how kind of inflation proceeds. If regions of the universe start at, say, this vacuum energy, the tendency at the dynamics at a particular point tends to be for the field to roll down this hill to the bottom, oscillate back and forth, and that transfers the inflationary energy into radiation and other particles that we're familiar with. So that kind of creates the heat in the hot Big Bang. So it's relatively easy now to take a model like this, crank it through some well-established code, and come up with a curve like this. And that's what's done in generating things like this plot. But that's all kind of boring compared to what happens if you come up with a slightly more interesting curve. And in general, we have no real fundamental understanding of where that v of phi curve comes from. So if you take a slightly more interesting curve, very, very different things happen. And that's what's going to be the subject of most of this talk. So today, take one example, mainly because it's fairly well understood and sort of under mathematical control what happens. If we take a picture like this, where there's a so-called true vacuum, that's a minimum here, and a false vacuum, that's a minimum at a higher vacuum energy. If you take some region of the universe that starts out in this false vacuum, the false vacuum energy will drive inflation. The universe will expand exponentially. And classically, nothing would happen. It would just, the field would just sit here everywhere. But quantum mechanically, it can tunnel through. And there's a well understood sort of theory behind that tunneling that was worked out by Coleman and DeLucia in the late 70s and early 80s, and sort of has been refined since. And it shows that what happens here is you create a bubble of this new phase. So it forms sort of a bubble where it tunnels through this barrier. And then inside that bubble, the field will roll down. And if the potential is correct, it'll slow roll down, and you'll get sort of the sort of inflation that you need to explain the observed universe. And if you take a slice through the space-time of that bubble nucleation, what it'll look like is this, where outside you have the original false vacuum. Then you've got some region that represents the bubble wall, this region of the potential. That's trapped energy because the field is draped over this region of higher potential. Inside, then, the field kind of decays down to the true vacuum value, where there can be reheating and generation of radiation and matter and galaxies and whatnot. So that's sort of what the bubble looks like if you slice through it. Now, what's quite interesting is that this sort of process is a quantum tunneling. It tends to be exponentially suppressed. So it tends to be a slow process tunneling through this barrier. Meanwhile, while this tunneling is happening, the background space is still inflating. And what that means is, although at any given point, if you just sit at some point long enough, you'll eventually eventually the field in your region will tunnel through, just like a radioactive atom decays eventually if you wait long enough. Because the inflation is going on exponentially in the background, you might form a bubble, but then by the time you form another bubble here, the background has continued to inflate. And it turns out that you'd never actually eat up the background inflating space. And you can sort of prove this relatively straightforwardly in a simple model where there are just two vacua, like the one that I've been showing. You can sort of show that the probability of being still inflating, that is in the false vacuum, or the fraction of volume that's inflating, similar thing, is e to the minus the number of nucleation events you expect in the past light cone of that point. So if you're here, you would be still inflating if you didn't have a nucleation in your past light cone, because these bubbles, which I didn't mention, expand at the speed of light. So if there's one in your past light cone, it envelops you. If there's not, it doesn't. And so you can see how many there are by just counting up the expected number in your past light cone. That's the volume of your past light cone, which in a sort of simple inflation model you can compute to be this, between some initial time and some late time. This is the Hubble constant, that's the expansion rate characterizing the inflating background. And lambda is the number per unit time per unit volume of nucleation events that happen. That's a quantum mechanical problem. So this is the fraction that should still be inflating if you have bubble nucleation going on between initial time t0 and some time you're interested in, t. And then what you can see is that if you take that fraction and multiply it then by the volume, the sort of background volume, that volume goes as e to the 3ht, that's the inflation, you get something that looks like this. It's an exponential, but as long as lambda is small, it has a positive index in here. So the volume that is, although this fraction you can see goes to 0, this gets big, so this fraction goes to 0. So the fraction that is left inflating goes to 0. The volume that is inflating increases exponentially with this exponential index. You can also show, in fact, that the distribution of still inflating regions is a fractal with a fractal dimension that is this thing here. So it's a very interesting structure where, although inflation ends everywhere, inflation still goes on forever. And I'll come back to that interesting kind of semi-paradox later. So the picture you actually get for the very large scale structure of the universe in a model like this is that there's this background represented by the black. These bubbles keep nucleating, but the background expansion drags them apart and creates more volume. and more place to nucleate more bubbles. And so even though you continually form these bubbles, unlike a sort of normal phase transition, this phase transition never completes. And this is just sort of a visual depiction of that. You can also imagine in a more complicated inflation model that if you go inside a bubble, there might be more bubble nucleations in there. And so you can sort of imagine this process semi-repeating, although each time you go into a bubble, you're going to lower and lower energy. So that's kind of a picture of eternal inflation in terms of this background space and these bubbles that are forming in it. If you want to depict it in a more sort of comfortable way for cosmologists, like a conformal diagram, you can put it together out of some basic ingredients. One is the background space, which is essentially de Sitter space. De Sitter space-time can be represented as a hyperboloid embedded in 4 plus 1 dimensional Minkowski space. So this is a 1 plus 1 dimensional hyperboloid embedded in 2 plus 1 dimensional Minkowski space. Time is going up here. So that's a representation of de Sitter space. You would then glue onto it a bunch of bubbles. These bubbles look like these sort of open light cones that represent the bubble expanding at the speed of light. And if you kind of cut this hyperbola down the middle and unwrap it and then shrink it into a conformal diagram, you get something that looks like this blue-gray rectangle. And the bubbles would then look like these diamonds that are stuck onto it. They extend above the top of this diagram because they have a lower vacuum energy and a larger horizon. They let you see more than if you didn't go into a bubble. So you end up with a structure like this. There's a kind of fractal structure at the top, echoing the fractal that I talked about before. So there's an infinite, although it looks like there isn't any volume of blue up there, there's actually an infinite volume of it, a zero fraction, but infinite amount up at the top there. So my claim is that everlasting bubble inflation equals infinite space-time. And I'm using infinite as if you integrate this, you get infinity in that sense. There are, in particular, future-directed world lines with infinite proper length in the inflating phase. So one of them would end up, say, here. So if you followed one of those world lines, you would find the inflating space just lasting forever. Again, in the sense that the integral along this thing diverges. It's also true you can show that the bubble distribution in the inflating background becomes stationary. That is, you can characterize, say, the fraction, or say that fractal dimension that I talked about for the bubbles as they eat up that background inflating space. That becomes stationary. So the universe becomes kind of a steady state. It doesn't look like it on this diagram, but up here it looks like a steady state, which I think is kind of philosophically interesting because in the early days of cosmology, there were the two models, the Big Bang and the steady state. And the Big Bang vanquished the steady state, which was just wrong, even though the steady state, in many people's opinion, was a much more beautiful theory. Certainly in mine, I think it was a more beautiful theory, and I'll come back to that. But it was wrong. But it turns out that maybe it wasn't, because the structure of this eternal inflation universe is just the steady state. They had particle creation. This has bubble creation, or maybe pocket universe creation, if we talk about the other modes of eternal inflation. But it's very much the same structure, and it seems to have come back and bitten cosmology. Now, that was one version of eternal inflation, the so-called open eternal inflation or bubbly eternal inflation or something. You could have it in other ways, too. For example, if you have a potential that looks like this, you can see that this ball doesn't know which way to go. So in some regions, it will fall down this way. In some regions, it will fall down this way. But just due to quantum fluctuations, for example, if nothing else. But because the field has to be continuous, you always have to have some region of this vacuum energy. And if it turns out that if this is flat enough, that will drive inflation. And so you'll get sort of a domain over here that's blue, a domain over here that's red, but you'll always have this inflating region in the middle, which is green. So you can never get rid of that once it starts. Another version of eternal inflation is stochastic eternal inflation, where if you take into account the quantum fluctuations in the field as it would generally just like to roll down the hill, if you go high enough up on the potential, those quantum fluctuations are are sort of comparable to the tendency of the field to just roll down the hill. And so what you'll tend to have is that although on average the ball will roll down in any given spot, it'll do a lot of jittering up and down so that the probability of it kind of rolling down a certain amount is small enough that it becomes overwhelmed by the exponential expansion. And so you find that the fraction of the universe at, say, this field value or above grows exponentially with time, just as in the bubbly version. And it's important to emphasize, I think, that the physics behind this type of eternal inflation is precisely the same physics that is behind the microwave background fluctuations if inflation is true. So there's nothing, so one of the things I would somewhat disagree with George about is that, it's true that the physics of inflation is very high energy, very difficult to test physics, but I wouldn't say it's untestable because that's exactly what we test when we look at the microwave background radiation and compare it to theoretical models. And if that physics is going to give us these sorts of fluctuations, I think it also gives us this potential stochastic eternal inflation behavior. Now, whether we can fully understand that is another question, but I think it is the same physics that leads to it. So I think, given what's interesting about those three diagrams is that you see that there's this eternal behavior, whether you're kind of at the inflaton, the field driving inflation, is at a minimum of the potential, whether it's at a maximum, or whether it's neither. So basically, if the potential is flat enough, you get this eternal behavior. But the potential has to be quite flat to have inflation at all. And so you actually have to work quite hard to get inflation that isn't eternal inflation. You can do it, but you won't do it sort of by accident. If I were to ask my 3.5-year-old son to draw a bunch of inflationary potentials, most of them would not be inflationary if you just drew a bunch of curves. But of the ones that were, I can guarantee you that almost all of them would be eternal inflationary as well. I haven't actually done this, nor has there been a rigorous study of this, but I think that's likely to be true. So I think if you have inflation, it's not unavoidable, but it's quite generic that you'll have eternal inflation and what I would call everlasting inflation, which produces an infinite space-time, whether you want to call it an actual or potential infinity or what. It is a space-time diagram that doesn't have any end on the top, and if you integrated the whole thing, would give you infinity. Now let's come to the question of whether the universe is spatially infinite or finite. Because it is true that you could start eternal inflation in a k equals plus 1 closed Friedman model, for example, where you might say that the universe's volume at any time is finite, even though it gets sort of unboundedly large. But I think this is actually not the right way to think about it, even in a so-called closed universe. Because when you ask whether the universe is spatially infinite, you have to face the fact that if we take general relativity seriously, the way we decompose space-time into space and time is up to us, and every way is equally valid as long as they're genuinely achronal surfaces. That means that no point on a surface can causally influence any other point. So, and the answer that you get to this question can actually depend on which slicing you choose. That is what you call space versus space-time. So an example of that is, this is just Minkowski space. Let's take some region of Minkowski space that's inside the forward light cone of some point, and we can draw a bunch of hyperbolas nestled inside this forward light cone. And we're welcome to call these equal time surfaces in general relativity. They're achronal, they're space-like surfaces. So those are a perfectly valid set of surfaces. It turns out that their geometry in more dimensions is just the same. It's an infinite hyperboloid. It's an infinite homogeneous negatively curved space. And so what we have here is, if you say, let's take this region that's inside the light cone, is it finite or is it infinite? Well, that depends. If you take the slicing that goes like this, that's one time, that's another time, that's another time. It's finite. It's a sphere that gets bigger. If you take this slicing, it's infinite. Neither of those slicings is more fundamental than the other. One of them might be more comfortable for a particular problem or question that you're looking at. But this slicing is a little bit more interesting in some sense, because in this slicing, things such as the curvature are uniform, whereas in this slicing, well, I guess the curvature is uniform here, but in other cases it won't be. In any event, either of these slicings is just as valid in general relativity. And so the answer to the question, is space infinite in this model, just depends on which space you're talking about, which foliation of space-time you're talking about. Now that's quite important because the structure of one of these bubbles, and George started to talk a little bit about this, is just the same thing as that so-called Milne universe that I just talked about. So as worked out by Coleman and DeLucia, if you look at the field structure that results from one of these bubble nucleations, you can draw in space-time surfaces of constant field. And what it looks like is that the field value here, where the so-called tunnel 2 field value, lies on this light cone. And constant field values kind of inside the wall lie on surfaces like this. And the field values down here form these surfaces. These surfaces, just like in that previous example, are space-like hyperboloids. They're infinite surfaces of constant curvature. The curvature gets smaller as you go down here. So it looks like a universe that is infinite, spatially open, negatively curved, and evolving towards smaller curvature, just like an open FRW model. Each of those surfaces has uniform energy density because it's a uniform value of the field, which determines the major energy density, which is the kinetic and potential energy of this inflaton field. If it gets to the bottom, then it can reheat, and the temperature and energy density of the radiation and so on will be the same along that infinite uniform surface. So in just the same way, although if you slice a bubble this way, you get a diagram like the one that I showed you before, if we take general relativity very seriously, I think we just have to say that that slicing is no more fundamental than any other one that we can make in the same space-time. The space-time goes on forever, as we talked about before. And this is a perfectly good slicing, and in that slicing, the universe is infinite at all times. And I think if we wanted to make it finite, we would have to cut this off at some point. There's no natural cutoff, and there's no particular reason to pick some slice along here that would cut off any of these equal field surfaces. One might or might not worry about the fact that bubbles run into each other. They do, as it turns out. Each bubble will run into infinitely many other ones. That turns out not to change this picture too much. If a bubble runs into a similar bubble, they will just merge together, and that won't change any of the questions about their finiteness or infiniteness. They get the same basic field structure way up the light cone. Similarly, if you run, and these are sort of numerical simulations of bubbles running into each other that my group has done. If you run two bubbles into each other that are different, so this is a kind of complicated picture with one vacuum that is the background that can tunnel in two different directions, over here or over here, to form this bubble and that bubble. Now when the bubbles run into each other, they're stuck with this big domain wall in between them, where the field goes through these values. That domain wall is going up here. The domain wall will accelerate one way or the other. In this case, it's accelerating toward the white bubble. But it turns out, and we showed that the equal field surfaces basically restore their hyperboloidal structure as you go up this light cone. So the fact that these surfaces are infinite and space-like doesn't change as a result of the bubble collision. That symmetry is sort of restored, and the basic structure of the bubble is just the same. And you can sort of make an argument that because this thing is accelerating and all that matters is sort of what the field is doing around here, that's sort of always going to happen. You're going to restore that hyperboloidal symmetry. So I think, in particular, what happens down here is not particularly relevant for seeing what the asymptotic structure of these things is as you go far away from the nucleation. It still has that spatially infinite aspect. Now, it's interesting also if you then, sticking with bubble collisions, if you look at a single bubble, it's sort of this infinite hyperbolic space. You can model that nicely with the Poincaré disk, which some of you may be familiar with. If you look at bubble collisions, the region that those bubble collisions could affect can be drawn as kind of little bites taken out of this disk. And even if you exclude those regions, even if you say, contrary to what I said earlier, that regions that are affected by a collision don't count, or you could consider regions where the wall accelerates inward, and so they're part of a different bubble. At any rate, if you color them black and exclude them, you still get infinite volume, because if you take, in the following sense, if you take a surface of constant radius, this is sort of a hyperbolic radius here, and integrate up the volume, the fraction, this is sort of a reprise of earlier, the fraction that will be still unaffected by a bubble collision will go to 0, but the volume at a given radius expands exponentially as you go out in a hyperbolic plane, and so you still get an infinite volume out here that is unaffected by bubble collisions. So even if you just count that, the volume of one of these bubbles is still infinite in that sense. And it has a sort of fractal structure as well. So in the most sort of clearly understood picture, the bubbles and bubble collisions, you can sort of do actual calculations of these things, and you find what the structure of the post-inflationary sort of reheating surfaces and so on, and they're generically infinite. It's also the case that open and topological and stochastic eternal inflation all have basically the same structure. Topological inflation is like that domain wall inflation that I showed you earlier, and stochastic also. They all have the same basic picture where you'll have some set of eternal world lines, and then you'll have some field of some field value at which there's some criterion where eternal inflation is not satisfied. So for example, where basically inflation stops, or where the criterion for driving eternal inflation fails, that you'd say not high enough on the field for stochastic eternal inflation to happen. And then past that, you'll have slow roll inflation until a reheating surface. So this can be the conformal diagram essentially for any version of eternal inflation. They all have basically the same structure. And again, these surfaces where the universe reheats are generically spatially infinite. And again, this is true even if the initial configuration of the universe, if it has one, is that of a closed universe rather than an infinite one. So I think my case at this point is that observational and theoretical cosmology strongly suggests inflation. The most significant rival is probably the cyclic model, but that's also future infinite, and I'll come a little bit more back to that. Inflation, I would say, is generically everlasting, although it's not unavoidably everlasting. If it's everlasting, I think it sort of necessarily implies that there's, I should have said infinite, well, it definitely implies this. There's infinite space-time, there's infinite time in some places, and there are unboundedly many infinite homogeneous spaces that you can talk about, such as the interior of the bubbles, or in general eternal inflation models, just the reheating surfaces. This still leaves the question, did the universe have a beginning? And even in eternal inflation, it's often assumed that there's a singular pre-inflation epoch, like there was in the original Big Bang theory. But it's not clear that you have to assume that, not clear at all. So the classic Big Bang singularity theorems that were developed in the 70s by Hawking and Penrose and so on, generally assume the strong energy condition, which doesn't apply when you have inflation. Inflation violates a strong energy condition. You can use other theorems that use only the weak energy condition, or similar energy conditions. And several have been proven that eternally inflating spacetimes must contain singularities, by which, again, they mean not all past null or time-like geodesics are complete. And there have been a few of these, one by Bourdais and Vilenkin, which is interesting, and a more recent one by Bourdais, Guth, and Vilenkin, in 2001. And these have convinced some people that inflation had to have a beginning. But it's very important with these theorems, I think, to understand exactly what they say. The singularity theorems certainly don't tell you that there's a singularity. They tell you that there's geodesic incompleteness of the space-time region over which the theorem's assumptions hold. Okay? Singularity theorems generally don't tell you that there's a singularity. They tell you that there's a finite geodesic or an incomplete geodesic. But in these cases, it's very particularly important to understand that they assume some assumptions about a space-time and then show that it's geodesically incomplete. But that can tell you that there's a singularity or that there's a failure of one of those assumptions that they made. So I'm going to give a few different constructions for how you might sort of undermine those singularity theorems and create a model, inflationary and some other ones, that are genuinely past eternal, where there isn't an initial sort of cosmological singularity. So one, and sort of the most obvious one, is that I described to you that the steady state model has come back to haunt us in this version of eternal inflation because it approaches this thing which is statistically a steady state. And I would say that sort of in the asymptotic future, you simply can't distinguish one time from another in terms of its statistical properties. So why not take this steady state approach by semi-eternal inflation and just make it exact? So really bring back the steady state model with its nice philosophical underpinning of this cosmological principle and perfect cosmological principle that the universe at all times is indistinguishable. So make that exact. So what would that look like? Well, in inflation, the, say, background space, the false vacuum, if you just pick this two-state model, inflates, so it becomes flatter and flatter. So let's make the spatial sections exactly flat. So this will be the flat slicing, so-called, of de Sitter space. That's the same space-time that the steady state model is based on. And you can consider bubbles formed between some initial time and some later time, t naught and t. And then the idea would be to send t naught to 0. So you can make t naught earlier and earlier. You can send it send t naught to minus infinity rather than 0. And what you can show is that there can still be inflation. So just as in the eternal inflation picture, the probability of randomly landing on a point that is inflating would be 0. But nonetheless, if you assume, you've got sort of a 0 times infinity, but in a fairly well-controlled way, I think, because it's the result of this limiting process. And you can show that all the same sort of statistical properties of the bubble, fractal dimension, and so on that you had in the steady state, in the sort of the future eternal case, can also be realized in this steady state, purely steady state case. Now, what's interesting is that you get you can then sort of work out what were these singularity theorems pointing to. And it turns out they were pointing to something interesting. So this is, again, de Sitter space. This is the full de Sitter space. The background that you're thinking about for this eternal model is the so-called flat slicing. Those are slices of space which you get with these lines that kind of go across the hyperbola like this. And you'll see that they kind of bunch up along this diagonal. This is a plane slicing through the hyperboloid diagonally here. What that tells you is that that flat slicing does not cover the whole de Sitter hyperboloid. It only covers half of it. And so if you take the region that is covered by this steady state eternal inflation model, it has an edge where that flat slicing ends here in the conformal diagram. So that is the end, that is the region that singularities that past directed world lines come to where they're incomplete, is right there. But then you can ask, well, what does that mean? The field value is perfectly continuous as you go back here. The metric is continuous, and everything is nice and continuous. Why not just extend it to this surface here and see what happens? You can, in fact, do that, and you find that what happens is you determine, once you extend by continuity the fields onto that surface, you determine what happens over here, which is that you have basically another copy of the same thing. So you end up with a full picture that looks like this, which has a very interesting property that you see here the bubbles are directed like this. The bubbles form, they're high energy here, they're low energy up there. If you look at how entropy increases that direction. So this is past, this is future. The weird thing that happens down here is that by the exact same argument, this is past and this is future. The bubbles are nucleating on these surfaces, they're growing, radiation's getting created somewhere, et cetera. So the future is pointed toward the bottom of the page here. Now, as far as I know, there's no fundamental law that the future has to be pointed toward the top of any page. So I think this is still OK. It does lead to an interesting universe, though, that is time symmetric globally. So if I flip this upside down, it looks the same. But locally, there's an arrow of time that is determined by the physics, in particular the physics of entropy increase. But really, sort of, it's determined only some places. Here, there's a local arrow of time. Back here, you've got de Sitter space. De Sitter space has no arrow of time. It's time reversal symmetric. And so you end up with this universe that is sort of has this statistical time symmetry while having a nice second law in local regions. And in either of these regions, it looks like steady state eternal inflation. So my feeling is that you may or may not like this model, but it has no particular basic sort of contradiction or problem. It has dynamics, the stochastic bubble formation. It has boundary conditions. Those are boundary conditions that you place on that big null surface that I was showing, that the field is in the false vacuum, that other fields are at minima, and that the Weyl curvature is 0 on this thing. So you can place those boundary conditions, and then that determines this cosmology. It also, I think, pleasingly has this underlying symmetry principle, the perfect cosmological principle, that I find nice from an aesthetic standpoint. So that's one version. There's a few more past eternal models we can think about. One is just a variation of this that I just made up the name, the bi-evolving universe, which is to say, rather than placing this kind of low entropy boundary condition on this null surface, why not pick a space-like surface? We could pick this one, or this one, or this one, whatever. This basic model has been worked out both by us. Carol and Chen have a very similar model, and I talked about it in a review paper later. It has the same structure. Whether you call it sort of past eternal or not is a tricky question. It's eternal. It's always inflating, and there's no cosmological singularity. One might argue that there's a sort of time 0, which is this curve, but one might argue that there isn't. So there's kind of a question of semantics here about whether you would call this a past eternal model or not, which I think unambiguously the previous one is. But at any rate, it's a non-singular cosmology where there are past and future directed world lines of infinite length, and is sort of always inflating. So it has those properties. We could also think of a cyclic model. Cyclic models get in trouble with the second law of thermodynamics in many cases, but not necessarily. So the cyclic model developed by Turok, Steinhardt, and collaborators is of the second category. I think it is OK with the second law, where you sort of locally dilute away entropy, essentially by inflation, honestly, and then you add it back in again by this process they called ekpyrosis. This model has this funny construction of two so-called branes bouncing into each other periodically. So if you look at sort of the scale factor of the different branes, one is blue and one is red, they clap together periodically, and that's where you create a bunch of new entropy. It gets diluted away during an exponential expansion period in between. And you can actually draw what this looks like embedded in a 4+1 dimensional Minkowski space. Looks like this, where you can see the kind of clapping parts here and here and here. It shares the same issue as the previous model, that it's geodesically incomplete. Here's the edge. It's a little bit, they argue that it's nicer. I argue that it's less nice because you can't smoothly continue to this point, right? You have this, there's no particular limit as you go to this point because it's basically oscillating. It also has another property that it also would form bubbles where the two things are stuck together and they would dominate the whole thing. But I won't go into that. So this is a model that exists. I think it is past eternal sort of by construction. Whether you like it better or worse or not at all is individual preference at some level, but it exists. There's also Penrose's cyclic model, which I don't really understand well enough to draw diagrams of it, but it has the same character of, I think, eternity in at least in one direction, and I would think in both directions. Another construction I wanted to talk about, although I'm running low on time, is the emergent universe. The idea here is that the universe is asymptotically static in the past. So it's kind of an Einstein static universe that sits there forever and then starts to inflate. And the goal here is having no quantum gravity or singular epoch. It's a model developed by Ellis and Martins. My concern with this model, I have to say I have trouble making sense of it because the universe kind of sits there forever and then does something. And philosophically, that's hard for me to say, why then? Why didn't it do it before, et cetera. More physically, I think I worry about quantum mechanics in this model. If you say, so the construction for this model is to have a field that's, so this potential goes forever that way. There's a field that's rolling along it forever, and then eventually gets to the end here where inflation happens. My concern about this is if we treat this as a quantum field, even if it's homogeneous, it will have a spread of values in the field value and in the field derivative. But the field derivative has to be tuned to an exactly particularly precise value in order for the universe to last for eternity. And if you say that the universe is a little field packet in field or field derivative, that packet will spread. And the parts in the wings will be ones that collapse or expand too far before they ever get to the end here. Now you can tighten up the packet in field momentum so that it lasts longer. That will spread out the field, the packet in the field. But if you go to a sort of delta function in field derivative so that it really could last forever without expanding or collapsing, then the field itself is arbitrary, right? And it's not clear that you can really say that that's a universe, right? Because the field has equal measure over all field values, and you don't know whether the universe you're talking about is inflating or infinitely far back that way. So I find it hard to come up with a self-consistent way of thinking about this as a kind of classical or semi-classical universe that doesn't involve quantum gravity or a singular epoch. So I would say that's a model that may be okay, but at least I don't aesthetically or doesn't quite make sense to me in terms of a past eternal universe. So just to summarize again, I think our actual understanding of cosmology that's come out of our physical theories, where inflation has kind of become a well-regarded necessary component of cosmology that explains the observed universe, has led to a likely picture of an everlasting universe. Now here I sort of disagree with George in that I think we can't ever really prove anything in physics. That's kind of a truism. But we can make things seem very, very likely to us so that we believe them. I think while we can't ever go out and see the infinite volume that is in these reheating surfaces, we can test inflation so that we believe it. We can, in principle, test eternal inflation by things like the bubble collisions, which could leave an observable imprint in our universe. And if we really believe inflation, or if we really believe eternal inflation, I think that should lead us to, at the same proportion, believe in an infinite universe. Just as, although we can never go inside a black hole and see what's in there, we still believe that we understand what happens inside a black hole because we understand general relativity. We believe it pretty well. It tells us what happens inside a black hole. We don't have to go there to believe that we know what happens. We can't prove it, but I think we can feel like we understand what's going on. I think if the universe is everlasting, it's almost certainly spatially infinite, at least in some set of coordinates, which are the natural ones for talking about cosmology. You could say our observed universe is kind of inhomogeneous and in spherical shells around us, or you can say that it's homogeneous. It's more natural in some way to say that it's homogeneous. And in these cases, it would be more natural to take the surfaces of homogeneity as surfaces of constant time, in which case they are open FRW surfaces. And I would say the universe is spatially infinite. Finally, the burden of proof, I think, is a little bit harder in terms of past infinite universes. There are reasons to think that the universe is incomplete to the past, but reasons to subvert those singularity theorems in certain models. And so I think there it becomes really a question of, can we construct a model that makes sense and that people like, where the universe is past eternal? And I think the answer to that is maybe. So that's what I have to say. Thanks.